In your post-quantum theory, is then the conservation of momentum something that is just emergent or not fundamental? Because if you're shooting a particle, let's say a planet, like you mentioned, the planet could go here or there. Does that not then send the planet off to another a slightly different trajectory than it was before?
Um, so, the, so there is a so the theory conserves momentum, but it doesn't conserve all. There are things which are not conserved in it, which would be conserved in a deterministic theory. So Noether's theorem, which is this famous theorem which connects symmetries with conservation laws, because we believe in time translate. Our theories of physics are invariant under a time translation, and they're also invariant if we move 3 meters to the right or 3 meters to the left. The laws of physics don't change, and that tells us that momentum and energy are conserved. Noether's theorem assumes that the laws of physics are deterministic and are given by a unitary transformation. If they're not, as in these theories, then you don't have the same connection between symmetries and conservation laws. And it turns out in this theory that because because you have lost this connection between symmetry and conservation laws, then energy does not need to be conserved. And so you can get something which may look like some kind of anomalous heating coming from these sorts of theories. Now, in general relativity, energy is very difficult to define in the first place. So, understanding what exactly that means to such a theory, where you don't really have a locally defined energy, that's another matter. But it's quite complicated in terms of how conservation laws are respected in such a theory.
Speaking of laws, you have a paper, I believe it's called The Second Laws of Quantum Thermodynamics.
Right.
So firstly, what is quantum thermodynamics? And then why are there multiple second laws?
Right. So we're always, at least when I was an undergrad, we were taught that thermodynamics is a theory that you get in the thermodynamic limit. In other words, I have a gas and it has many particles, and I take the limit that the gas is, the volume goes to infinity, and that's what thermodynamics is. It's that theory of large systems. But you can ask, what happens to, if I just have, say, a single gas molecule or a single quantum system, does it still obey things which look like the second law? And can I still define some laws of thermodynamics for those systems? And it turns out you can. So, for a single particle, the entropy also has to increase. But it turns out there's a whole bunch of other quantities which has to increase as well. So I can think of, in some sense, the second law of thermodynamics as placing a restriction on what will happen to my system as time goes on. So I know that the entropy has to increase, but there's a bunch of other entropies that you can also define, and it turns out those also have to increase as well. There's something called Renyi entropies. There's all kinds of entropies which are different to the standard one. And it turns out those all have to increase. And what happens is, as I have more and more particles, and as I make my system size grow larger and larger, it turns out that all these other second laws and all these other entropies become equivalent to each other. And so in the thermodynamic limit, I only have one entropy, but on the small scale, I have a whole bunch of other entropies, which turns out they also obey some kind of a second law.
We corresponded over email, you and I spoke about Flaminia, who's also working on quantum information and gravity. And I was curious to what the relationship between her approach is and yours.
Right. So she's, her and some of her colleagues have proven various theorems about what happens if the gravitational field is classical. And they've done it in a more general framework than we often work in. So they haven't made an assumption, for example, they haven't assumed that matter obeys the laws of quantum theory, they've allowed, they've considered more general sorts of interactions. And in fact, you can, there's all kinds of machinery that has been developed called, say, it goes by the name of generalized probabilistic theories, which is a huge class of theories which go beyond quantum theory. We don't know if they actually exist, these theories, or whether they are well-defined or not, but you can certainly think about the kinds of, some of the properties they may have. And it turns out that, so I mentioned these experiments we've proposed where we show that if gravity is fundamentally classical, then it has to be stochastic. It has to have randomness. And they've essentially, one of the results, for example, is that even if we go beyond quantum theory, if gravity is classical, then it somehow, will still have to be stochastic, even if we're able to modify the laws of matter. So if we go beyond quantum theory for the matter distribution.
And what about Chiara-Marletto? What about constructor theory's relationship to yours?
Yeah, so that's another example where, where she has looked at theories which go beyond quantum theory, and I guess in both cases the claim has been that it rules out the classical theory of gravity, but usually there's some assumption, for example, of reversibility or an assumption of determinism. And so what these theorems tend to show is that if we have a classical theory of gravity, then they have to be irreversible or have some sort of indeterminism or randomness in them. So I think this is kind of establishing that if gravity is classical, it has to be stochastic. I think from their point of view, that is so unpalatable that for them, and for maybe many other people, it is enough to rule out the classical theory of gravity. So if you believe that the laws of physics should be deterministic, and you don't believe in fundamental randomness, then you probably are unlikely to believe that gravity could be classical.
I also spoke to you over email again about a no-go theorem by, I believe it's Marletto. I believe it's her.
Right.
Or maybe she referenced it, but either way, can you talk about what that is and how yours escapes it?
Right. So, there's a no-go theorem due to Marletto and Vedral, which essentially, in some sense, it's related to this Feynman thought experiment we mentioned, where we have a particle that is in some superposition and it produces a gravitational field. And if I can measure the gravitational field, then that would seem to determine which slit the particle goes through, and therefore rules out having an interference pattern. You can imagine that you have some other theory which is not quantum theory, and what they've shown is that that argument still holds. But again, there's that loophole that I mentioned, where if the gravitational field has some randomness in it, then those sorts of arguments don't rule out classical gravity in that case. So I think the big question is, do we believe, well, first of all, for me, this has now become an experimental question. We should go out and measure whether the gravitational field has randomness in it. If it doesn't, then we've essentially ruled out a classical theory of gravity.
Is it conceivable that we can perform this measurement within the next 20 years or so?
Right. I mean, in some sense, we already have placed bounds on such a theory. So, we can, it's just a question of how much. And I feel like we need to better understand the theory before I would be able to tell you, exactly what those numbers are. Because what we've essentially been able to, it seems that in order to correctly predict how much noise you need in the gravitational field, you need to go, it's a fully relativistic calculation. So you need to go beyond the weak field limit. And so we're still performing those calculations.
Mm-hmm. Now, Bohmian mechanics was something else that I mentioned to you, and I'm curious to see the relationship between yours and, what's the relationship between your theory and Bohmian mechanics?
Right. I mean, there's not an immediate one, but there is.
Does yours rule out Bohmian mechanics, for instance?
Well, it's hard to see how you could rule out Bohmian. So I guess we discussed before this kind of philosophical side of physics, in particular in terms of the measurement theory of, in terms of these various interpretations of quantum mechanics. And so it's depending on your flavor of Bohmian mechanics or many worlds interpretation or etc. Many of them are equivalent from a physics point of view. Although they're flavors of those interpretations or those, theories, where there is a physical difference between, say, Bohmian mechanics and some other interpretation of quantum theory. What I will say is that the one thing I like about these classical quantum theories is that you don't need you don't need the measurement postulate of quantum theory. So I think one of the reasons we have all, this discussion of interpretations of quantum theory is because it's very unsatisfying how quantum theory deals with measurement. And we seem to have the standard rules of quantum theory where things evolve deterministically, and then we perform a measurement and we get, the state supposedly collapses and we get a random result. And that's not very well understood. On the other hand, in this theory of gravity, in some sense, the gravitational field is doing the work for you and is causing states to localize and for the wave function to collapse. So because the gravitational field is in some sense always measuring where the particle is, one doesn't need to invoke the measurement postulate of quantum mechanics. So in some sense, it's its own interpretation of quantum theory.
And before I let you go, I'm curious, what has been the reception since your Quanta article from the public and then from the physics community?
Actually, I have to say that the people have been quite open to it. I feel like there's definitely been, especially from the relativist community. Well, I would say even from string theorists, I feel like there's been an openness. Often it's of the form of, well, I don't believe that gravity is classical, but I'm glad that you're, exploring the consequences of that. I'm glad someone is doing that. So that's I feel like that's at one end, and so there haven't been many people who most people have been, I think, quite engaged with it. For me, what is the most exciting engagement I've had is there's this community of people who are interested in actually performing the experiment. And so that has been exciting in the sense of, I think what we're going to see is a large scale effort to test the quantum nature of gravity. Because I think for a while, there was always this assumption that in order to test quantum gravity, we needed to go to the Planck scale. We needed to go to incredibly high energies before we could ever make a prediction about gravity. And what we're learning now is that actually there's all kinds of things that you can test for in terms of quantum theory of gravity, which do not require Planck energies. So, for example, can graviton, testing whether gravitons can create entanglement, that's something that that doesn't require Planck energies, and which we hope is maybe feasible within the next decade or so. So I think that's been the most exciting, this kind of experimental effort.
Well, it's been exciting. It's been illuminating to speak to you. Thank you. I appreciate you coming on to the podcast, and I look forward to speaking with you again.
Likewise. Thanks very much. Appreciate it.